So this isn't going to work quite as well, but we're going to try it this way. I'm not as good at recording videos using PowerPoint, but with the Google down, do what we can do. First of all, we're going to try to go through as much of the notes as we can today. I'm not going to be here next class. You guys are going to look at the answers to worksheet 1, and you're going to do an online lab where you explore the wonder that is gas laws. Now, science is not a bad answer either, but gas laws. So, all right, let's see how we're doing. We're going to talk about kinetic molecular theory today and do gas laws, which is a whole lot of algebra, and then everyone's favorite tree ends up at the end. The stoichiometry comes back again. Lots of moles in this chapter, just like your uncle. So the first thing we're going to talk about is what the heck is kinetic molecular theory. So we're going to do a visual exercise that occurs in your brain. So you're going to close your eyes for a second. That means you're going to have to put your phone down, Monbeam, okay? Close your eyes for a second. I want everyone to imagine that we are in the gym and you have a blindfold on. That's why your eyes are closed. Close them. I see your eyes. You're looking at me. I could literally see your eyes. Or close them. Gabriel wouldn't close his eyes, Michelle. That's who I was talking to. Now he's giggling again. And so, on the count of 3, I tell the entire class with blindfolds on in the gym to run. I don't care which direction Caroline goes, or which direction Vivian goes, or Ali goes, but you go as fast as you can. Some of you do what immediately? Collide. I was looking for collide. And then there's people like Sonia who just magically miss everyone. Stop looking at me. Your eyes are closed. And you run across the room, Sonia, and you just hit the wall hard and then bounce off. But Sonia's tough. She turns around and starts sprinting again. And at full speed, she collides into Brennan and destroys Brennan in a glorious collision. And you hear Brennan go, "Oh!" That's like the loudest noise he's made all year. It's, "Oh!" And he falls to the ground. This is a great visualization of kinetic molecular theories and gas molecule. You can open your eyes again. Gabriel, you can open your eyes. Open them. Good. All right. His mask is over his eyes. I can't believe how many people just looked. So anyway, when we talk about kinetic molecular theory, we're talking about how gas particles move. And I really like that visualization of Sonia like accidentally missing everyone as everyone else is colliding. She hits the wall and she bounces off. All right? Everyone heard her hit the wall because she hit so hard. And then she bounces off and then she collides with Brennan and there's a lot of energy transfer. And so we typically imagine gases as being perfect. And there's 5 rules for, what page am I on right now? 180 what? 185, thank you. There's 5 rules for kind of describing what a perfect gas looks like. Now, what is the likelihood that a gas is actually perfect? No. No is the likelihood. Some gases are more perfect than other gases. We call them noble gases. And then other gases are pretty good. And then some gases are outright terrible gases, like lead. Is lead a very good gas? No, it's a solid, it's a metal. That means it's not really a gas. At this temperature, if you warm up lead to a nice 3,000 Celsius, and it's a gas, and it follows the descriptions we're going over here now. But hopefully you're not around while it's 3,000 Celsius, because that's a bad day. So the 5 rules, the 5 parts of kinetic molecular theory. Okay, that was French. The 5 parts of kinetic molecular theory. Part number 1. Gases consist of objects with a defined mass with 0 volume, though. That's impossible but exciting. In reality, we're talking about individual atoms or molecules. How big is an oxygen molecule? How many atoms are in an oxygen molecule? 2. O2. So it's just 2 atoms, and it's insanely tiny. So tiny, we might just go ahead and say its volume is 0. It does have a really, really small mass also. And so it's flying across the room right now, bashing into your head, going into your lungs, moving around. In fact, you can hear me right now because of the gases. Number 2, gases follow a straight line path. Where's the gases? I was going to throw stuff at you today. Can we see a ball? It's there. It's there? Oh, give me that ball. Don't hit her in there. Okay. So gases follow a straight line path. The only problem with that straight line was it was a curve because that ball has a lot of mass, doesn't it? So when she throws it back, that was a much better curve than mine. The curvature of the particle's path is heavily curved because of the mass of the particle, right? That gas particle is so heavy, it follows a heavy intense curve. If it was a lighter particle, its curve would be a lot less, right? So let's see if I can write on here. Okay, yeah, they follow straight line motion. Because they have almost no mass, their arc is almost flat. And you don't really worry about the curve, the arc of a gas particle, unless you're comparing it to like a huge distance, like miles. Because then after a while, it's actually curved. All collisions are elastic. I want you to write some math here. It's very complex math. Ready? 4 plus 3 equals 6 plus what? 1. You guys are smart ones. Yeah. The energy in the system is conserved. That doesn't mean everyone has the same energy. When Sonia is sprinting into Brennan, the energy that Sonia has slams into and gets transferred into Brennan, and thus the noise as the collision occurs. None of the energy is lost. It just keeps bouncing around. Okay? All right. Number 6 is where it really starts to fall off the rails with reality. Gas particles do not interact with each other. That's the idea that when Destiny and Riddy collide at like full speed, Riddy's not going to like grab onto Destiny for dear life afterwards. Like, that really hurt, and grab on. She needs to just bounce off and keep moving. And that's where our example falls apart. That's where a lot of gases actually fail. Your noble gases tend to stay gases no matter what, except at the extremes. But what about like water? When is water a good gas? Can somebody give me a temperature at which water is a good gas? I got the boy with the mask on his eyes. Yeah. At 100? Higher than 100. Yeah, when water is above 100 degrees Celsius, then it tends to be a gas really well. It flies around, hits things, bounces off of things, and doesn't, what's the opposite of boiling? Condense. It doesn't condense. The opposite of boiling is condensation. And so if you're above 100, the water molecules hit, they have too much energy, and they fly away. If, however, they're below 100, they often hit and go, I think I'll just stay right here. They actually bond with the surface. And so we're going to pretend that all gases are perfect. A good word for perfect is ideal, that they behave in a perfect or ideal fashion. And then the last thing is that the gas phase of the average kinetic energy is proportional to the temperature. That kinetic energy is proportional to temperature. That funky little fish symbol I just made is the proportionality sign that says if the temperature increases, so does the kinetic energy. There's no equation that we're actually going to use for that. However, most people have a bad imagination when it comes to temperature, but Theo has some insight on that. Yes, Theo. Well, let's add a number 5. There's 2 ones. Renumber the numbers. Is that better? He just groaned at the idea of renumbering the numbers. Is that the number 5 that was labeled 4? Grazie. So, let's imagine that Manny and I have particle hands. All right, particle hand. Ready? How hot is your hand? What's the temperature of your hand? Make it vibrate. Particles vibrate like this, like this, like this, like this. Get a little closer to me, like you're gonna smack me around. Okay, smack. Good, good, good. All right. So my part. Don't stop. No one said you can stop. Okay. You need to do right-handed. Okay. So who is vibrating faster? Me. So when we collide, energy is being transferred, right? And eventually, let's stop because it's starting to hurt. Eventually, we would come in sync because every time I whap his hand, energy is transferred and we both felt it. And so he's going to gain energy and he's going to start to go faster. And I'm going to lose energy and I'm going to start to go, and eventually we're going to be in sync. You're just about the best at in sync, but there's bad. Good job. And so when 2 surfaces touch, they exchange energy until the surfaces are in sync, where the exchange of energy becomes pretty much non-existent. All right? Now, it's more complicated with complex objects like you, me, a cell phone, where there's things going on inside that are making energy, that are making heat. Let's not think about that. Let's keep it simple. You have a rock. The rock is hot. Put the hot rock in water. The hot rock's vibrating. The water's vibrating also. Right? The hot rock vibrates and gives energy to the water. The water vibrates faster. The rock vibrates slower. Everyone eventually vibrates at approximately the same speed. Temperature is really the particle vibration. So when we take your temperature, right, when Gabe's mom's like, open your mouth, here comes the thermometer, like, right, sticks it under the tongue, they're measuring what his temperature is, how fast the particles in your body are vibrating. What's the dangerous temperature you don't want to be at? What's like the max you want to be at before things go wild? You're about 104 to 105. If you get above 105, you start to have seizures. Yeah. 98 is pretty typical. Some people are 97. It's a good idea for you to take your temperature tonight when you feel normal, just so you know what your normal is, because average normal is not your normal. None of you are normal. All right? I think that's true of most people. Normal people are boring. Yes, Mason, you're not normal.
Technically, normal people are not normal because most people are not normal.
They're the average. And who wants to be average? Manny raises his hand. Yeah. Shoot, how do I insert a page? I can't insert a page in the middle of the presentation, and I can't go back because this, I can't because I'm recording. If I go back, it'll record over the previous slides. It like records the audio on each slide. It's stupid. But I care about you, Michelle, so I'm doing this for you. Let me just pause and think for a second. Yep, I'm committed to this slide. I'm going to talk about this slide. All right, we'll do some extra stuff in a minute. But so temperature is how fast these particles vibrate. We're going to assume those 5 things are true. Those 5 things are that particles have mass but almost no volume. We call it 0. That particles travel in a straight line. That when particles collide, energy is conserved. What's the word in there for energy is conserved? It has, maybe you don't know the use of this word like that. Maybe you think of your pants or waistline or something like that. What's the word in there? What? Elastic. Circle that word because it's not being used in a way you're probably used to. Elastic. I'm on the previous page. I just can't go back. I can't go back. So I think rule 3 said that energy is conserved. It is elastic. And then 4 said when stuff collides with the container, it doesn't interact with the container. And then 5 said that temperature was proportional to energy. True? All right, those sound like good multiple choice questions in a test in the future, okay? So make sure you've reviewed those terms well enough to be surprised by the weird usage that I put them to. One of the first instruments created to kind of measure gas stuff is the barometer. And boy, is it invented a long time ago. This is when Mr. Shangri was born. In 1643, it was invented by Evangelista Torricelli, who is actually a student of a guy named Galileo. Have you heard of Galileo? No? He liked to stare through telescopes and see that, he saw the moons around Jupiter. Yeah, and drew some conclusions people didn't like. So Galileo's student is Torricelli, and Torricelli invents the first barometer. And his first barometer is actually made of water, and it is 36 feet tall. That's a pretty big barometer. But let's kind of focus on the smaller barometer that we're looking at here. We have a long test tube that was completely filled with mercury. It was completely filled with mercury. And a beaker that was mostly filled with mercury. And then Heaven plugged the test tube full of mercury, and she turned it upside down, stuck her hand down into the beaker of mercury, because Heaven's a little, she likes to have fun. And then she took her thumb off. So it was underneath. And so she's got a complete seal, so no air can get into there. But I know you haven't played with mercury because the world is afraid of mercury nowadays. But what happens is that the weight of the mercury is a metal, it's heavy, it's a liquid, and it gets pulled down by gravity. And at the top, we get a bubble of nothing. A space that contains 0. What do we call nothing? A vacuum, right? Not the one, but a vacuum is the absence of everything. You might have like a friend like this. That was a little dark, wasn't it? Sorry about that. I was looking at you too when I said that. And now you feel like I am. And so, as gravity pulls the mercury down, that vacuum also appears. And that vacuum pulls the mercury back up. And the gravity pulls it down. And the vacuum pulls it back up. And the mercury pulls it down. And after a while, Heaven notices that the mercury stops going down as it reaches equilibrium. So it goes like, woo! Okay? It doesn't make the noise. You tried to listen. You didn't get it. And it doesn't change. And then you get like a little marker, and you put a little mark. And then every day you go by and you check the mercury level. Sometimes it's up higher, sometimes it's down lower. And you're like, what the heck is going on? And she notices something. She notices when a rainstorm comes through, the level goes down. And when the air is perfectly clear and bright and blue outside, the mercury level goes up. In earth science, some of you learned about high pressure fronts and low pressure fronts. Those terms high and low always confused the heck out of me. Because I was like, is the air higher today? Is that why it's not raining? Is the air lower today? Where do these two terms come from? And they come from this instrument. When it rains, we typically have low air pressure. The mercury level is lower. When it doesn't rain and it's perfectly clear outside, the mercury level's higher, and that level changes depending on the amount of air pushing on this pool of mercury. If there's more air pushing, there's more force, then that mercury gets forced back up the tube. If there's less air pushing on it, then the mercury comes down the tube. And it actually changes based upon the amount that's in the air. Yes, Mason, I ignored you for about a minute and a half.
And I understood why my question was stupid.
Go. Probably not stupid, just ahead of its time.
No, I got confused.
Evelina, you should leave. Okay. I don't know why, but you feel like you need to leave. Your entire body language is goodbye. Um, the mercury level would change with the air pressure, which of course means that Torricelli is practicing witchcraft. So yes. Now he was one of those guys that kind of had to keep his findings under wraps, if you will. And you're really comparing the weight of the air pushing on the surface of the mercury to the weight of the mercury being pulled down. And those two things reach a balance. And here is a slightly different image of the same thing, plus you get to see his mustache. And just, that is a fantastic mustache. Good work, sir. Really nice. I mean, plus he's got the soul patch. Good job. So the atmosphere is pushing on the mercury, which is forcing it up. The mercury is being pulled down by gravity, and it balances out. And so we measure the height of the mercury in millimeters. We measure the height of the mercury in millimeters. And I had one of these barometers at my first school. I was always so afraid that someone was going to break the barometer, because then the school would be shut down for weeks while it gets cleaned up. We don't have any mercury in this building. None that I'm really talking about. So the barometer works really well. They're just a little bit dangerous because they get broken open, mercury spills. They didn't shut down and seal rooms up and stuff. They actually had a mercury spill in Fairfax a couple years ago where the teacher had a beaker of mercury out and letting the kids play with it. It's totally harmless to play with mercury like once or twice in your life, but to like live with mercury, that's when it starts to get dangerous. And one of the kids stole the beaker of mercury, walked around the school playing with it, dropping mercury all over the place, and contaminated the entire school. They shut the school down for 6 weeks, and everyone went to a different school for 6 weeks, and they split the student body up amongst 4 local high schools. How do you like that ending? We went from that's a W for Manny to like, I don't want to go to Parkview. I don't want to go there. I don't really want to go there. Sir, yes.
Is mercury actually as dangerous as people say it is, or is it like nuclear power where people just get scared of it?
It does cause madness if you inhale mercury vapors on a regular basis.
Okay. So,
Yeah, there's actually there was an issue with that. We're not allowed to sell mercury inside the United States. Keyword inside the United States. And so the power plants, when you burn coal, you capture all sorts of things in the filters. One of the things they capture is mercury. And so they have these mercury building up in these filters, which they weren't allowed to sell inside the United States. So they realized they could sell it outside the United States, and they were selling it to developing African countries where gold mining was still just taking off.
oh.
And mercury has a weird property that it dissolves gold. Mercury dissolves gold. That's weird, right? Like if you take your uncle's gold ring and drop it in mercury, it dissolves. And he gets really mad. And so what they were doing is we're selling this mercury to these gold panners, and the guys would take the mercury, they would like crush up a bunch of rocks, like a whole bunch of rocks, then they would pour the mercury in there, add some water, and stir, and then you could sift out the remaining rocks, throw them away. You could then boil off the water, and then you just had the mercury and the gold. And then they would boil off the mercury, inhaling the mercury vapors, putting the mercury where? Yes, that's terrible, but putting the mercury back into the air, which is why they had the filter at the coal factory in the first place. And then these people were going insane because they were inhaling mercury vapors also. So that's a terrible story. You're welcome. It's now banned. You can't do that even. You have to. There's like a special storage process that I don't understand, nor do I need to. As a high school chemistry teacher. Manometers or manometers. So here we have two manometers. I don't know if the pointing actually shows up. It doesn't show up. So the one on the left is not open. The two on the right have an open hole. You see the difference? So they have fancy names. The one on the left is a closed manometer. The other two are called open manometers. And they're open to the atmosphere. So if Amanda heats up this bulb that has a gas in it, it's going to cause those gas particles to move faster. They're going to push on this mercury, which is going to get pushed up the tube. All right? But since it's sealed, can the mercury escape? No. And whatever gas is trapped over here is going to push back, and there'll be a balancing act between the hot gas that's pushing the mercury and the trapped gas that's not hot. And there'll be this balancing act, and Amanda could repeatedly do tests on gases she's trapped. On this side, though, it's gas that she's trapped versus the atmosphere, and if she overpressurizes or overheats, what's going to happen to the mercury? It's going to shoot out. Yeah. And I worked in a lab that we actually worked with open manometers in college, a physical chemistry class, which is a really cool lab. Terrible class. Terrible. It sounded like it was going to be cool, but it was all the math of the electron moving around the nucleus. It was calculus plus chemistry. The only people in the world that like that are named Ayub. All right? And the rest of us are like, you took calculus and did what with it? Run away. Okay? All right. There are multiple units for pressure. We need to know how to use atmospheres. Highlight that one or circle it. We need to know how to use millimeters of mercury, which comes from the Torricelli barometer. Try saying the word millimeters of mercury. A little bit of a tongue twister. So people, instead of millimeter, we have 745 millimeters of mercury minus 35 millimeters of mercury. Instead, they just say Tor. Because who invented that barometer? Yeah, Torricelli, so they named him after Torricelli. Then we have 101.3 Kapaz, which is not Klingon. And let's cross out this one, the Poseids. The Poseidons are not going to be used by us. That is pounds on a square inch. But take a second with your finger and draw a square inch on your hand. If you're like me, a square inch actually lasted for a second because my capillary action's so bad, there's actually a square like lasts for a second. So on that hand, there is air pressure, pounds and pounds of air pressure pushing on it. How many pounds are pushing on that square that is an inch by an inch? 14.69 pounds of air pushing on it right now. Can you feel it, Dominique? Can you feel the pressure pushing on your hand? You're used to it. You're used to it. Do any of you sleep under a weighted blanket? It's a weird class question to ask. No one? Usually there's like one. Okay, couple people. After a while, you don't notice it, do you? You just feel like, oh, I'm being hugged all night long. But it doesn't feel heavy after a while because you get used to the weight. Same thing here. Your entire life, you've had this pressure on your body. You're used to it until it changes. How many of you have been up high, like in a real mountain? Not the Blue Ridge, but like in the Colorado Rockies. And the air pressure changes significantly, and sometimes it hurts. Like your head hurts, you get lightheaded and stuff like that. Because the pressure drops, there's less air up there. Did you get lightheaded? Did you get lightheaded? Did you get lightheaded?
Only one person was like
I vomited.
I vomited. He went there, not me.
We were in Morocco, and we went up to the rigid range. Like, you could see Spain.
You could see Spain from Morocco. That's across the Mediterranean.
There's a point. At the most
Yes, but it's across the Mediterranean. Yeah, the Strait of Gibraltar. Yeah. Wow, I knew something. Did you hear that? That was pretty good. That was fun. I accidentally said something correct. I gotta sit down. I'm lightheaded.
Yeah, we were at the peak, and we were looking out, and it was really beautiful. and I started to feel woozy.
Was it from the height or from like? Do you have
from
a
the
fear of
height.
heights?
It was from the height.
Yeah, I don't like heights either. I put on a VR goggles once, and I was at the space station, and I looked down at the Earth while wearing VR goggles, and got lightheaded because I was so high up. Yeah, I was like, this is not good. Kilopascals, the kPa, a pascal, which I can't type on here. It's going to irritate me a lot. Oh wait, why don't I grab the pen instead of handwriting? The pascal is actually a kilogram of weight on a meter squared. That's not true. Oh, I can't undo. It's not a kilogram. It's a newton. Sorry, it's a newton of weight on a square meter. There's a joke there. Do you want me to tell you a bad joke?
Yes.
Do you know what a newton is? A newton is amount of force. It's how hard it is to accelerate a kilogram by a meter per second. But so, 3 people go to play hide and go seek. Einstein, Isaac Newton, and Pascal of the triangle variety. Heard of Pascal that made the triangles, the 3, 4, 5 triangle, stuff like that? Remember the 3, 4, 5 triangle? Yeah? Okay. Let's pretend you do, Manny. It'd be good. Okay. And so, Einstein closes his eyes and says, everybody hide. And then Pascal runs away giggling and goes and like hides under a desk or something. Newton, being a brilliant genius, pulls out a piece of chalk and draws on the ground a square that is 1 meter by 1 meter and then stands on it. And then when Einstein opens his eyes, he looks at him and goes, Newton, I found you. You're right there. And he goes, no, you found Newton over square meter. You found Pascal. That's pretty bad. Yeah. That's a nerdy math joke / physics joke. I just stole one of Dr. K's jokes that she uses. Okay. So we need to be able to convert between these units. I'm going to scratch out this PSI. We never use it. So 2.18 atmospheres. Let's say I needed to change that to kilopascals. I look at that list of equivalencies. How many atmospheres, how many kilopascals in that equivalency? In that whole list. This is equal to this, is equal to this, is equal to this, is equal to this. How many pascals and how many atmospheres? It says 1 atmosphere is equal to 760 millimeters of mercury, is equal to 760 torr, is equal to, and since they're all equal to each other, we can just write the 2 that we need as a ratio and then convert to kilopascals, and my brain is telling me this is the answer since I did this 2 blocks ago, okay? So we just use dimensional analysis to convert. That's a pretty standard thing, isn't it? You need to know those 3 equivalencies. I know there were 4 of them, but 2 of them were the same, weren't they? 760 and 760. We will use all 3 with regularity. Here is the first gas law. It is called Boyles Law, and it was discovered by Guillo Sacks, not Robert Boyle. But Robert Boyle worked with Guillo Sacks, and Boyle comes before Guy, and therefore Robert Boyle got credit when they published, because you publish in alphabetical order. We'll talk about Guillo Sacks in a little bit. He gets his own law. Here's the entire idea. You have a can. Right? I have a can for sound effect purposes. It is sealed. When I squeeze it, it gets smaller, assuming that I can overcome the pressure buildup. So when I squeeze it, it gets smaller. If I add enough force or pressure, it will contract. More pressure, smaller can. Cool? We're not letting any gas out. We're not changing the temperature. We're only messing with the pressure and the volume, which brings us, oh, look at those. They're moving. That's exciting. Which goes, how do we use our lungs? We use our lungs using the Boyles Law equation. You probably remember when you were first born and your mom or dad, or maybe it was the doctor, was explaining how to use Boyles Law to breathe. And so Caroline, baby Caroline, was like, I don't know what to do. And the doctor said, make your rib cage as big as possible. Do it. What happens when you make your rib cage as big as possible? You inhale, right? Close your mouth and try it for a second. You can't, can you? Because as you do it, the pressure drops. It's kind of dangerous to actually push yourself to do that, by the way, because you can screw with your lungs. Don't do that too much. You're breathing through your nose. That's cheating. Yeah.
I think it'll mess with your ears first before your lungs.
Your ears are the pressure equilibrium point through your station tube. Yeah.
It hurts.
Yep. So when you open your lungs up wide, the pressure drops. And then since there's less pressure in your lungs and more pressure out here, air goes where? In. You drop the pressure in your lungs by expanding them, and then there's a difference in pressure. Air fills the drop in pressure. And then to reverse that, breathe out as hard as you can. I want you to do this. Breathe out as hard, every ounce, like you gotta get it all out. What do you have to do to get it all out? Go extreme. Do you actually, got lightheaded. You actually kind of have to like bend over to get all the air out, don't you? You have to like squeeze your lungs as hard as you can. You squeeze the volume down and you increase the pressure when you do that. And if you increase the pressure, then the air flies out, right? So this is Boyle's law. Pressure times volume equals pressure times volume. This is our first equation, P1V1 equals P2V2, right here. Yes, you have to know this is a law. Yes, you have to know it's a Boyle's law. Yes, you need to, I'm going to highlight it because it's important. You need to know it's an inverse proportion. Inverse proportion means as one goes up, the other goes down. And so in this example, Riddy has a 1.5, why am I choosing green? That's a weird color for Riddy to use. Riddy has 1.5 liters of Freon at 56 torr. And then she changes the pressure to 150 torr. Does she change the temperature? So that part doesn't matter because it's not changing. And she wants to know the new volume. How do we do this math? 1.5 times 56 equals 150 times V. We divide the 150 over, don't we? We multiply the left side, and then, see your left side? Yeah. Multiply the left side, and then divide to solve for the missing volume. And the missing volume is, after multiple calculations that I have done 1,000 times, 0.56 liters. If the pressure is increased, the volume is decreased. Yeah. Preguntas, estudiantes. Sí, señor.
Is Boyle's law, given the fact that it relates to volume, does it also then prove the proportionality of pressure and density?
No. Except maybe in gases. Because in solids, it's a lot weirder. So. Charles Law. Charles went to Virginia Tech, which is just a stupid way of remembering, he didn't really, that it's all about V's and T's. All right? Charles Law is about volume and temperature, and I always remember this terrifying Tinkerbell balloon I bought for my daughter when she was 5 or 6. Anybody watch the Tinkerbell cartoons in here when you were a little kid? I was a couple unexpected hands over on that side. I was expecting a lot more in this region here. So I bought her this Tinkerbell balloon inside the Party City. You know the one I'm talking about, the one that used to be next to Food Line, no, next to Shoppers. And I come outside, and it was 20 degrees outside, 70 degrees, oh, Fahrenheit, that stupid scale. And Tinkerbell, like, immediately went like, "Ugh," and collapsed. Because the temperature dropped, so the volume of the balloon dropped, and she looked depressing and sad. And then when I brought her home, she warmed back up, and she reinflated to her normal volume, and then was creepy for the next 4 months as she floated around my living room until she had an accident. She was always staring at me. It was so creepy. We do need to actually use the new and amazing temperature scale called Kelvin. The temperature scale for Kelvin is very easy to convert. It's just a simple addition problem. No weird 9/5 or anything like that, or 5/9. You take your temperature and add 273, and you're done. So the room right now is room temperature. Do you agree? Yeah, and it's about 25 degrees Celsius according to this thermometer I'm not reading. Okay? It's 25 degrees Celsius. What is 25 plus 273? It's 298 kelvins. It's not any hotter than it was a second ago. We're just on a different scale. All right? That's about 77 on the Fahrenheit scale. So the room is warm for most people. All right? When we use any temperature, we must use the Kelvin scale. What if it's in Celsius? Switch it to Kelvin. What if it's in Fahrenheit? You're on the wrong classroom. Right? You have to use the Kelvin scale every single time. So Riddy has a 2-liter balloon. It is at 298 kelvins. She then cools it to 278 kelvins and wants to know the new volume of the balloon. How do we solve this amazingly difficult math problem? We cross multiply, don't we? And we solve for the volume, and I believe it's 1.85 liters. That's what my memory is saying. I would appreciate it if someone would just verify my mental memory. That conversion was actually figured out by a guy named Lord Kelvin, which is why it's Kelvins, the Kelvin scale. Lord Kelvin was born William Thompson. Eventually, he earned the title Lord when like his uncle died or something, and then he became a lord of an estate. And he was Lord Kelvin, and he's an interesting guy because at one point he had the record for the highest balloon flight, hot air balloon flight. He went up in a hot air balloon, and he just about died because people didn't know if you go too high, there is no air. And he went up super high, and as he passed out from a lack of oxygen, he pulled the cord to let the hot air out and came back down, thankfully for him. Yeah. He held the record. That was a pretty exciting story for him. He's back. Sorry. Okay, I feel like it needs a drawing. There we go. He's back. It's Avogadro. It's pretty good. Pretty close. He could have paid me for the drawing. It's so good. So Avogadro is a different volume, and notice that the pressure is PPP. It's the same pressure each time, isn't it? That's the same pressure in all three. What's different in here? There's 1, 2, 3. Say there's 1, 2, 3, 4, 5, 6 particles. Now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 18. We went from 6 to 12 to 18 particles. We're now talking about how much stuff is in there. Better known as this. Okay? Jake has a balloon. He puts some air in the balloon. It's a small balloon. Jake blows more air in, and the balloon gets, and then he blows in more, and it gets, and then he lets the air out, and it gets. Yes, Avogadro's law is basically just comparing volume to the amount of stuff inside. And of course, If you're discussing moles, you're going to use the letter N to represent moles. Because that makes sense, right? Moles is spelled with an N, right? It's because M is mass or molality. We don't talk about molality. That's a dirty word. No, it's just a different thing we haven't gotten to yet. We haven't gotten to molarity either. Both of those sound like words I'm just making up, though, don't they? Molality and molarity.
Molarity sounds like a real word. I've never heard of molarity.
Well, then you won't know if I've made it up until we get there. You could use the Google machine. So, Jake has a 2-liter balloon, and he has blown 5 moles into it. Good job, Jake. And then he blows 5 additional moles into it, and now it's got 10 moles inside the balloon. What is the volume of Jake's balloon? The volume is in fact 4, assuming the balloon like stretches consistently and stuff like that, which we would just pretend it does. Or maybe he's got this in a big old piston, and the piston just expands and contracts as you push more air into it. All right, that is Avogadro's law. It deals with moles and volume. Now we have Guillo Sacks Law. Guillo Sacks was actually one of the guys that did most of the work and then shared his ideas with others at the time, and they figured it out. I like Guillo Sacks Law the best. So we have this can. It's got a fixed volume and it can't get any bigger. And then Caroline throws it in the fire. Can the can get any bigger? No, but the energy transferred in is going to make the gas particles do what? Go faster and faster and faster and faster and faster and faster. Sorry, Michelle. Until it explodes or just leaks, right? Like, and everyone just stares at it disappointed, hoping for a real big pop, but it just leaks. I didn't realize earlier that my can was open, and I let someone step on it, and they crunched it. And I was confused because I didn't pick a particularly heavy person, and I was like, why is my can crunching after 20 years of doing this demo? And it was open. So the air escaped. Now I gotta like pop it open and bang it out from the inside. Alrighty, let's read this question. Tori has a 10-liter container of gas. The pressure is 50 liters. Now, the only thing I don't like about the way this question is worded, it should say somehow the volume can't change. It should say the volume can't change in some sort of way. We often would say that she has a rigid container or something like that to kind of indicate that the container's not a balloon, the container's not a piston, it's something that can't expand. And so that's kind of missing from this wording. So Tori has her rigid 10-liter container at 90 kPa and 25 degrees Celsius. Can I use 25 degrees Celsius?
No.
I need to convert that to kelvins, which is 298 kelvins. Tori wants to know the new temperature if the pressure jumps to 101.3 kPa inside. How do we solve for this? There's a lot of talking going on over there, but it eventually breaks down to we cross multiply and cross divide a whole bunch of times. We move the t over there, move the 298 there. Wait, I don't want the 90 there. We move the 90 down there, and eventually we have the t on the left side and everything else on the other side. One of the keys, though, to any type of problem like this is the thing you're solving for has to be on top. It has to be like t over 1. It can't be on the bottom. The easiest solution of this, and for some reason a lot of you don't know this, I don't know like what happened in algebra, but this is the same equation. Toilet paper is equal to toilet paper. TP over TP is this equation again. I just flipped it over. It's the exact same equation, and it's easier to solve for the new temperature because the temperature is already on the top. And all we would have to do is move that mysterious pressure to the other side in our cross multiplying. I believe the temperature is 338 according to my memory. I don't have a calculator. I have what happened second block stored in my head. The jokes were better then, sorry. So, does it make sense that Tori has heated the can up? What is happening to the pressure? More pressure, so Tori probably made the can hotter. Okay. All right. Let's start combining some of the things together with the combined gas law. It should really be called we combined a couple of the gas laws, but not quite all of them because we got lazy law. But that's a mouthful. So just the combined gas law. It is Boyles Law, PV equals PV. It is Charles' Law, V over T equals V over T. And it is Guillo Sacks Law, P over T equals P over T, all merged into one. Read the question, what are we trying to solve for? Temperature. So since we're trying to solve for temperature, and that's on the bottom, I'm going to preemptively write the entire equation upside down so that it's just slightly easier to solve for the temperature. Let's see, 300 kelvins over 6.32 atmospheres and 3.5 liters is equal to unknown new temperature times 4.15 atmospheres and 4.7 liters. And so the three circles mean so. The temperature equals something I can't remember. Let me grab a calculator while people write. Bless you, don't do that again. 300 times 4.15 times 4.7 divided by 6.32 divided by 3.5. 265 kelvins. How many Celsius is that? Subtract 273. That's negative 8 Celsius. It's not outer space cold. Outer space is like negative 269 Celsius. That's pretty cold. Oh, wait a minute. Earlier, you and I, Manny, did a demonstration of temperature, right? Now, let's imagine that your hand, stick it out there, has a temperature and it needs to be vibrating, right? Good. Now, we take the temperature down slowly until it reaches 0 kelvins. Pretty close. His finger is vibrating just slightly. Can you stop it from moving at all? Show me.
I mean, that's how it is.
No, but I need no movement.
Not possible.
It's very hard to get to 0 movement. When we talk about 0 movement, we mean the atoms themselves are not even moving. At 0 Kelvin, there's no motion at all. Is it possible to stop the electrons, the protons, and the neutrons from moving? No, it's not. And we have gotten down to, I think the record is 10 to the minus 34th kelvins, which is really, really close to 0. Things get weird down there. We're kind of on a time crunch. Maybe I'm going to tell you a bunch of stories next time. I'll just fill up the whole block with stories. Of course, I won't be here next time, so we'll do that the time after that time. The ideal gas law. It is inappropriate, Amanda, for you to use the mnemonic device Parkview equals no real talent. Don't do that, okay? That is not nice to say Parkview equals no real talent. I don't want you to do that. I prefer to rewrite this equation. Dang it, already messing up. I want you to rewrite this equation. R equals PV over NT. PV and N and T, you know those. We've experienced them for all of 45 minutes. What is P? Pressure. What is V? N, of course, is, and T is. What are the units for, let me change colors. What's the units for temperature? Kelvin. What's the unit for N? What is the unit for V? Liters. We will use liters, primarily liters. If it's in milliliters, you might want to switch to liters. And then pressure. Pressure could be a bunch of units, couldn't it? Pressure's annoying because sometimes Michelle uses atmospheres, but Riddy likes kilopascals, and then Vivian likes torr, and just to be ornery, Brianna likes millimeters of mercury, even though that's the same as torr, and she just likes to say millimeters of mercury because it's her birthday. Happy birthday, Brianna. And if we plug in any combination of gas, what's your favorite gas, Evelina? Pick a gas.
I like chlorine.
Fluorine?
Chlorine.
Chlorine. So if she has chlorine gas, which is used to kill people, if she uses chlorine gas and she throws in some data, like she has a mass of chlorine gas, can you convert masses into moles?
Yeah.
So she would have the moles. What temperature is your gas at? Room temperature, hot, cold? Tell me, Evelina. Room temperature. So it's 298 kelvins, isn't it? Right? And then is it like this pressure or high pressure or low pressure? Tell me about your fictional chlorine.
It's low pressure.
It's low pressure. So we could plug in whatever the pressure is. The only missing piece is the volume. R is a constant. You haven't encountered a lot of constants in your math life yet. Maybe you've encountered a 3.14152674555505555. I just made those numbers up. I don't know. No. This is not a show-off competition. This is a competition for people that pretend they know things, not really know things. Is pi a constant? Yeah, there's a bunch of constants out there. Here is the universal gas constant. This is the value for R. But you said constant, and then you put 3 numbers up. You're kind of a jerk. Do you agree? That's kind of a jerk move? Well, again, it's not my fault that I forgot who I said liked atmospheres. Riddy, were you atmospheres? So if Riddy likes atmospheres, this is going to be her value for R. It's liters, it's moles, it's kelvin, it's atmospheres. So then the pressure that would be plugged into here would have to be measured in atmospheres. Whereas I think Vivian liked torr. So she's going to use 62.36, and all of her P's are going to be in torr. Okay? I think I said, Brianna, you like millimeters of mercury? Do you remember that millimeters of mercury and torr are the same because millimeters of mercury is kind of a mouthful? So you could also use this number, but because you don't like to write torr, you would write mmHg. It's the same number, it's just a different symbol. And then kapaz, I don't remember who liked kapaz. Was it Destiny? You? Well, can we be? Because it's a physics equation. Yeah, kappa is what physics people use. So let's look at a question now that we've dealt with it. So Connor has some hydrogen in a gas cylinder. The volume of the gas cylinder is 8.56 liters. That's a lot of liters, yeah. He is at 0 degrees Celsius. What does Connor need to do with his temperature first? What is 0 plus 273? Good job. You did the math correctly. It is, in fact, 273 kelvins. Connor has measured his gas cylinder in atmospheres, 1.5 atmospheres. And now we need to look at the R choices. What are our R choices? We had 3 R's. We had 0.08206, we had 8.31, and 62.36. Take a look at Connor's pressure. Which R are we going to use? Why? We're going to use the first one because Mr. Murphy said so. No, because it has units. Its units are liters, atmospheres. Oh, atmospheres. Look at that. Yeah, we're picking the unit. We're picking the R that matches our units. And it also still has moles and Kelvin. So we plug all these in, we can solve for N. So we have pressure, 1.5. We have a volume, 8.56. We don't have N, so I'm just going to leave the letter N in there. We have R, 0.08206. And we have the temperature, a balmy 273 kelvins. And then we solve for N. Yeah, I think it's 0.56, but I'm going to check. Still a little winded from the extreme air blowout I did. That was kind of like too extreme. 0.573 moles of hydrogen. And if we have these moles of hydrogen in a balloon, could we figure out how many grams are in the balloon? Yeah. Yep. One of the things we regularly forget to do when we do stoichiometry, et cetera, is compensate for the weight of the air inside the thing. But thankfully, the weight of the air is less than our scales can even measure. Our scales go 2 decimal places. There's air inside the beaker that's adding to the weight, but it's less than 2 decimal places worth of air, so it doesn't even show up. All right. Other gas laws that are pretty self-explanatory. Dalton's law of partial pressure literally says if you have a bunch of gases and you add the pressures together, you'll have the total. That's not bad, is it? That's a pretty good one. I like that one a lot. These examples are a little tedious. We could add this pressure, and this pressure together and have the total pressure. True? The most common use of this is when we collect a gas over water. So let's say that Ali is making oxygen gas in a test tube, and that test tube is over top of water. There's going to be a little bit of water floating around in there also, because water turns into a gas. And so the total pressure is going to be the pressure of the oxygen plus the pressure of the tiny amount of water. And so if Ali wants to know how much oxygen, he has to subtract it out of the total. He has to subtract the water out of the total. And we'll talk about that a great deal in the future, just not today. Volumetric ratios. Again, we're going to bring out Avogadro's law, but we're going to use it in a completely new and exciting way. When we had balanced equations, what did these coefficients represent in our past? What could we write with the coefficients? Moles. What letter represents moles in Avogadro's law? N. So what we can do is we can write 12 liters of water over 6, because the coefficient is 6, is equal to what volume over 7? Where did I get the 6 and the 7 from? The water and the oxygen. We can use the coefficients as our N values. That's an exciting new trick. Yeah, that's gross, isn't it? 7, oh wait, no, it's 14. Because 12 divided by 6 is 2. 2 times 7 is 14. I math. 14 liters of oxygen. All right. The last thing we definitely needed to do today, and we got there, is standard temperature and pressure. I think we agree that this is a pretty nice air pressure. Everyone kind of likes 1 atmosphere. It's the amount of pressure on your body right now. When Sonia goes into the high mountains, she's going to do some mountain climbing. The pressure drops pretty significantly. In the Rockies, the air pressure is about 85% of what it is here. Like if you're in Colorado, it's about 0.85, which really causes some unique issues. Water doesn't boil at the right temperature. Water boils at about 90 degrees Celsius, so the water's not as hot as you need it to be, so it takes longer to cook. Since the water's not as hot, you have to cook it longer to get enough energy into there. Boiling and cooking is all about just putting energy into food. If the water's not as hot, it takes longer to get the right amount of energy in there. It's like slap, slap, slap versus slap, 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 slap. So you have to slap them slower but longer. So this is the weird part though. Standard temperature is freezing cold. What is not in the air at 0 Celsius? Water. And so we picked this standard temperature so that when Ali captures his oxygen over top of the water, if he cools the water down to 0, the water that's in the air will condense and he'll have just oxygen inside that space. And so at that temperature and pressure, we could take PV equals nRT, there it is right there, and plug in the pressure, 1 atmosphere standard, the temperature, 273 Kelvin, the appropriate R, and the amount of moles, say 1, and we find a relationship that's really handy. 1 mole is the same as 22.4 liters of gas at standard temperature and pressure. So if you have that temperature and that pressure, you can use that ratio instead of going through the entire gas law rigmarole. You don't have to pull out any gases, any fancy gas laws. You can just go divide by 22 or multiply by 22 to switch between liters and moles. That's pretty fancy. I think that's where we're going to end today. Ooh, that says how many atoms. Everyone hates that question. How would we deal with atoms? We would have to use Avogadro's number to switch it into moles. And then once we've switched to moles, it's at STP. We could deal with volume. Let's end there. Do worksheet 1. You're going to look at the answers next time. And then you're going to do a lab on your Chromebooks. Yay. You're going to do a FET. A FET is a digital lab. It works pretty well. Bye, Michelle. Hope you're having a good day and that you